Very good morning to all. Myself, Dr. P. Gopinath, Assistant Professor, Selection Grade, Department of ECE, KIT, Kalanyar Karunanidhi Institute of Technology, Coimbatore. Today we are going to discuss the subject is digital communication. In this digital communication, baseband transmission is a vital role for our digital communication. So in this part, intersymbol interference and Nyquist related criteria conditions we had seen already. Today we are going to see that correlative coding. That is a correlative level coding. Here adding ISI, that is a intersymbol interference, is a important drawback of our digital communication process. So we will overcome that. We are utilizing first one is a Nyquist criterion, then second one is a pulse shaping, then third one is we are utilizing this type of level coding techniques. So in this ISI to transmit the signal in a controlled manner. Since ISI introduced into the transmitted signal is known, its effect can be interpreted at the receiver. A practical method of achieving the theoretical maximum signaling rate of 2W symbol per second in a bandwidth of W Hz. So the maximum bandwidth we have set as 2W. Then using realizable and perturbation tolerant filters. In this level coding having a three types. First type is called that is a duo binary signaling. So duo means that is a doubling of the transmission capacity of straight binary system. So this is the block diagram illustration. So here input we have denoted that is a BK. Then delay element is there. Then next one we are analyzing that is a channel performance. That is a Hutch Nyquist of F. Then next we represent the sampling at time t equal to KTB. Then finally we obtain output sequence CK. So in this case, that is a binary input sequence, we represent BK. So if BK value is 1 or 0, based on that we obtain AK value. So that is a binary input sequence BK for uncorrelated binary symbol 1 or 0. If symbol BK is 1, that is a plus 1. AK value is plus 1. Then BK is 0, the value is minus 1. Then after obtaining AK, we have calculated in CK. So CK utilizing that is a formula is CK equal to AK plus AK minus 1. So this is the waveform, that is a duobinary signaling Nyquist channel bandwidth. So that is a W equal to 1 divided by 2 TB. So in this derivation, we obtain that is a channel response, that is a Hutch of F. That is a Hutch Nyquist of F, that is 1 plus exponential of minus j 2 pi ftb. Then Hutch Nyquist of F, we have to write, that is a 1 we write e power j pi tb in plus e power minus j pi tb. So that value is called is 1. Then e power minus j 2 pi ftb we have expanded e power minus j pi ftb and multiplied with e power minus j pi tb. So we know the formula e power I theta equal to cos theta divided by, that is a e power I theta plus e power minus I theta divided by 2, that is equal to cos theta. So we apply that equation so that we obtain 2 Hutch Nyquist of F cos pi of tb, that is a exponential of minus j pi of tb. So here based on bandwidth condition, that is a Hutch Nyquist of F, that is equal to 1. For the limit value is minus pi to minus 1 divided by 2 TB to plus 1 divided by 2 TB. So that is illustrated modulus of f less than or equal to 1 divided by 2 TB. Then remaining values 0, that is a otherwise condition. So after obtained, we are represent the frequency response. It may be reach the maximum value is 1. So we illustrate using a sin theta function, that is a sin pi t divided by tb divided by pi t divided by tb, plus we have expanded, that is a sin pi t minus tb divided by tb divided by pi t minus tb divided by tb. So we have write tb square sin pi tb pi t divided by tb divided by pi t tb minus t. So this is the equivalent frequency response curve. Then along with we represent, that is a phase angle equation. So in this case, that is a H1 of t, that is a Nyquist condition, that is a decay as 1 divided by modulus of t square, which is a faster rate of decay than 1 divided by modulus of t compared to the condition 1 divided by modulus of t square. That is encountered in ideal Nyquist channel. So this is the basic formula. We obtain AK, that is a AK represent estimate of original pulse. In this original pulse, we calculated AK equal to CK minus AK minus 1. So here we obtain, that is a decision feedback and propagate pre-coding. These are the three stages for the above block diagram. So first one is a decision feedback. In this decision feedback, technique of using stored estimate of previous symbol. Then propagate is a drawback. Once error or mad, they tend to propagate through the output. That is a pre-coding. In this practical means of avoiding the error propagation phenomenon before the duo-binary coding. So in this duo-binary signaling, we further classify, that is a precoder we are using with precoder and without precoder. So based on that, here we represent differential shape, that is a dk, that is equal to bk exclusive r of dk minus 1. So that is a dk equal to symbol 1. Either bk or dk minus 1 is 1. Symbol 0, that means otherwise. Decay is generally denoted pulse amplitude modulator producing a corresponding two-level sequence, either plus 1 or minus 1. So this is the basic formula. CK already we known, AK plus AK minus 1. So in this case, duo-binary signaling, CK how to obtain means based on BK value is 1, at the time data symbol value is 0. Data symbol value BK is 0. So we obtain CK value is plus or minus 2. So in this duo-binary signaling, modulus of CK equal to 1, that is a random guess in favor of symbol 1 or 0. So these are the two cases, modulus of CK less than 1 and greater than 1. So less than 1 case, BK value is 1. Greater than 1, at the time BK value is 0. So this is the block diagram illustration. That is a pre-coder stage should be performed in this functional diagram. So in this module should be connected. That is a module to adder. That is a delay element should be connected. So this module we have called it as pre-coder. Then after pre-coder, remaining as usual steps we have followed. So next one is a modified duo-binary signaling. This is second type. So in this type, non-zero at the origin, that is undesirable cases. That is a subtracting amplitude modulated pulses spaced the bandwidth to TB second. So that is a CK is a basic formula AK plus AK minus 1. That is a H W of F, that is equal to H Nyquist of F of 1 minus exponential of minus j 4 pi ftb, because we represent the signal value is plus or minus 2. So that is equal to 2j H Nyquist of f, that is a sine 2 pi ftb that is a exponential of minus j 2 pi ftb. So after applying sin formula, so that is a h of iv of t, that is equal to 2tb square sin pi t divided by tb divided by pi t 2tb minus t. So this is the basic functional diagram of modified duobinary signaling. So in this module, first module is a pre-coder stage. The next one is a pulse amplitude modulator stage. Then third one is a modified duobinary conversion. So in this stage, first one is a pre-coding. So pre-coding, we obtain the formula dk equal to vk exclusive of dk minus 2. So if the symbol vk or dk minus 2 is 1, at the time we produce output is dk value is 1. So otherwise the symbol value is 0. So this is the magnitude and phase response of modified duobinary signaling. So here modulus of ck equal to 1, the random guess in favor of symbol 1 or 0. So that means a modulus of ck greater than 1, the symbol bk is 1. If symbol bk is 0, the condition is modulus of ck less than 1. So this is the generalized form of correlative level coding. So modulus of ck equal to 1, that is a random guess in favor of symbol 1 or 0. So various classes we represent in this tabulation should be illustrated. So which technique we have followed, that is a duobinary or modified duobinary stage. So finally we obtain the formula h of t. So that is after applying channel equation h of t equal to summation n to n minus 1, that is a wn sin of t divided by tb minus n. So remaining see in a next session. Thank you.